17 analysis of IR and NMR spectrum experiment. It is a dry lab. In this experiment, or the purpose of the experiment, is to be able to interpret IR and NMR spectra. The IR and NMR spectra can be used to determine purity of the sample. It can be used to monitor progress of the reaction, check for completion of the reaction. It can be used to identify unknown sample. In the IR spectrum, the scale of the or the region of the light that is used is from like 400 to 4,000 per centimeter, which from 400 to 1,400. I always just say make it simple. If you're using the 400 to 4,000 and then use the 1,400 here, is the fingerprint area in this area, and we have the major functional group. The peak set appears based on the major functional group. It's going to appear between 1,400 and the 4,000. Now, mostly all organic compounds, they have absorption in this region of the light, and the absorption is shown by peaks, and the location of the peak, the strength of the peak, is used to interpret what type of functional group the compound or the organic compound contains. So if you check the exact frequency where the absorption is taking place, it depends on the mass of the atoms that are involved and the strength of the bond. The strong bonds usually have the peaks on the higher energy level, like OH. You have a strong bond, and the peak it appears at 3,300. For alcohol, a broad peak with a round tip, that's the specification for the OH. And then you have a CO double bond that appears at 1,700. The reason I use this because is a peak that it's been studied in previous experiments, and we have prior knowledge about that. So if the design of the experiment is based on change in dipole moment, when you have a polar bond like CO double bond or OH bond, the peaks are stronger than if you have like a CC triple bond. And that peak can show a peak signal around 2,200, but is a shorter peak or a weaker signal. The difference between like the narrow signal or broad signal, the broad signals, they are shown often for bonds that or compounds that they have OH or NH. OH and NH, due to the hydrogen bonding, it would show like a broad peak, broad signal. And then the strong signal versus weak signal, a strong signal when detector is detecting based on the absorption is increased based on the polarity of the molecule. The polar bonds are going to have stronger signals, and the non-polar or less polar bonds are going to show weaker signals. To interpret IR spectrum, we are just going to follow a few steps, and with these few steps, like we want to check a carbonyl group present in the molecule. If the carbonyl group is present, a signal between 1,600 to 1,800 would be shown in the spectrum. Now, if that carbonyl group is coming from carboxylic acid around 1,700, for amide, that number, it would be much lower, because amide forms like two resonances, and one of the resonances is going to look like this. And then we have the CO bond between single and double bond. So the signal would show at much lower number. For aldehyde, this peak appears with around 1700. Depends if it's conjugated. If it's conjugated, it would show at lower number. If it's attached to electron withdrawing group, it would show at higher number, but still around 1700. And for ketone, would also the CO double bond show around 1700. Now, the exact location is going to vary based on the groups around it. So if you have electron withdrawing group attached to CO double bond, it would show at a higher number. So we see in the case of the ester, we have that number around like 1730, 1740. For ketone is around 1700, but if you have a conjugation, like you have a CC double bond right next to it, the frequency for the CO double bond is going to be lowered from 1600 to like a 1680. If it's super conjugated system, like what we had in the past, if it's a super conjugated system, then this number is going to even be dropped to like 1650. If it's super conjugated, that means we have multiple pi bonds around the CO double bond. The difference between a ketone and aldehyde is that for aldehyde, we have a number set. So we have a 1700 and 2800 and 2700. So we have all three of them. We know we have aldehyde. For ester, it's just one peak around the 1730 to 1740, and another peak for CO single bond shows around 1100, or a number between 1000 and 1200 or 1300. It depends on, again, if there's electron withdrawing group next to it or not. This peak is going to be a strong peak. That's what we know, because it's a polar bond as well. For carboxylic acid, we have a peak around 1700 for the CO double bond, and also a peak for OH. This peak is going to show, the signal is going to be very broad, going from 2500 to 3500. So from 2500 to 3500 is going to overlap with the CH bonds. So it starts from 2500 and going to 3500. So you see like something very broad, and around 3000 you would see this overlap of the peak from the CH bonds. Okay, this is coming from the carboxylic acid. Is going to be very broad, because for alcohol, if we have the OH, it starts after the 3000 and is around 3300. For OH coming from carboxylic acid, it starts from 2500 and it goes to like 3500. So if the compound contains CO double bond, the CO double bond, these are all the carbonyl compounds. It could be carboxylic acid, which we know that is a number set, 1700, and the broad peak. If it's amide, it's unusually low, so around 1640, 1650. And if it's a primary amide or secondary amide, this NH bond would show around 3300. If it's aldehyde, we have a number set, 1700, 2700, and 2800. If it's ester, there would be a peak around 1730, 1740, and one around 1100. And for ketone, you have only one number, is not a number set. So it's just one number for ketone around 1700.